In the first lesson to this section of our STEM instructional program, we introduced you to the four forces that impact the flight of an aircraft. In this lesson, we're going to focus on the concept of weight as it applies to aircraft. These same concepts will also apply to helicopters and lighter-than-air craft. We're going to address weight as a scientific concept, which is differently than we typically think about it. The weight of an aircraft is a downward aerodynamic force that opposes the force of lift, the force that must be overcome to have the aircraft leave the ground. To take off, the lifting force must be bigger than the force of weight. To maintain an altitude, the force of lift must be equal to the force of weight. Because of that simple concept, weight is a critical factor in the design of an aircraft and in planning for flights. When we typically think of the weight of an object, we put it in terms of how much something or someone weighs, either in pounds or kilograms. In the areas of science, technology, and engineering, the term weight takes on a different meaning. For a scientist, an engineer, or an aircraft designer, weight is a force caused by the gravitational attraction of the Earth. That force is, by definition, a push or a pull. The first thing that we need to examine is the difference between the term weight and the term mass. The mass of an object is the sum of all of the atoms, particles, and molecules that make up that object. The difference between mass and weight causes a lot of confusion. Put simply, mass is the amount of matter in an object. Weight is a measure of gravity's effect on that mass. Move to a different location or a different planet, and the object's mass will remain the same, but its weight will change. To better understand the concept of weight, we need to look at how we would weigh an object. When we weigh an object, we place it on a scale. The scale gives us what we mistakenly refer to as weight. The reading is actually an estimate of the mass of the object we are measuring at that specific location under a specific pull of gravity. All three of the scales that you are most familiar with all depend on the acceleration of gravity to exert a downward force on an object. Although not a recommended experiment, if you were to take apart your bathroom scale, you would find a spring. In order to get a reading on the scale, the spring is compressed. To cause that compression requires a downward force. In other words, the spring compresses until it reaches the point that the downward force exerted by the mass at the acceleration of gravity at that location is equal to the upward force exerted by the spring. In effect, the scale is an application of Hooke's law. The reading on the scale gives you an estimation of the mass of the object by compensating for that location's acceleration of gravity. If there were no gravitational acceleration, there would be no push, no downward force. Because we have been conditioned to read weight in terms of kilograms or pounds, we forget that it is impacted by gravity. The force of weight, or what scientists refer to as weight, is the product of the mass of an object and the local acceleration of objects due to gravity. Gravity, or gravitation, is a natural phenomenon by which all things with mass are brought toward or gravitate toward one another, including planets, stars, and galaxies. The force of weight in an object, then, would be the product of the mass of the object and the acceleration of gravity. Using the International System of Units, mass would be measured in kilograms, and the acceleration of gravity measured in meters per second, or second squared. The term used to express the combination kilogram meter per second squared is referred to as a Newton. Why is weight important to the study and design of aircraft? We usually think of weight as being a constant value. There are two reasons why we need to think of weight as a variable in the field of aviation. One, the acceleration of gravity is not a constant value in the locations in which an aircraft operates. And two, because the mass of an aircraft is changing as it operates. If both variables in the force of weight equation change, then the force of weight also changes. The first variable is that of the acceleration of gravity. The acceleration of gravity is dependent upon the distance between the centers of the two objects, in this case the center of the Earth and the center of the aircraft, and the mass of the two objects. That acceleration acts to pull objects toward their centers of mass. As the aircraft climbs to cruising altitude, it changes the distance between the center of the Earth and the center of the airplane. The farther apart the two objects are, the less the acceleration of gravity will be. For this lesson, we will be using a Boeing 737 airliner, the most commonly flown commercial aircraft used today, as our example. For our 737, whose cruise altitude is 9,145 meters or 30,000 feet, there is a measurable decrease in the value of g. While the impact of the change in gravity is small in relation to that of the change in mass, it is something that aircraft designers and engineers must take into consideration when looking at aircraft performance. If we take a look at aircraft that are designed to fly at much higher altitudes than a commercial airliner, the differences in the value of g and the force of weight become even more significant. As the relationship of the mass of the Earth and the mass of the aircraft does not change that much, even with the mass lost through fuel use, the impact of changes in gravity by itself has only a minor impact on the aircraft. The second variable that we will look at is changes in the mass of an aircraft. The mass of the aircraft is the sum of the masses of the materials that the plane is made of, all of the mass of the passengers and their luggage and carry-on bags, and the weight of the fuel. For a typical 737 aircraft, 32% of the mass of the aircraft is fuel. That fuel is expended as the aircraft operates. For a 737, the engines burn 750 gallons per hour. That equates to 5,000 pounds or 2,267 kilograms of lost mass per hour. The impact of mass becomes more pronounced when we talk about a different type of aircraft. In this case, a Northrop Grumman B-2 Spirit bomber. A significant component of the bomber's mass is the bomb load. Unlike a commercial airliner, at some point in the flight of the bomb load will be released. This will result in loss of overall mass of the bomber over a relatively short period of time. For the B-2 bomber, it could lose up to 18,000 kilograms, or between 12 and 20% of its mass, over a very short period of time. As the mass drops, the amount of lift required to keep the aircraft at a specific altitude at a given speed decreases, resulting in an imbalanced force acting upward. Without a corresponding change to the aircraft's controls to change lift or thrust, the aircraft would rise. To complete this look at weight in aviation and flight planning, we're going to look at a flight of a Boeing 737 airliner from Cleveland to Los Angeles with a cruise altitude of 30,000 feet or 9,145 meters. A non-stop flight from Cleveland to Los Angeles takes 4 hours and 31 minutes. During that period, the aircraft had used 22,583 pounds or 10,239 kilograms of fuel. As the chart shows, the aircraft takes off from Cleveland with a takeoff mass of 70,535 kilograms. As Cleveland Hopkins Airport is at an altitude of 241 meters above sea level, the acceleration of gravity would be 9.806 meters per second squared. That would equate to a takeoff weight in excess of 691,000 newtons. For each minute of flight, fuel is used, reducing the mass of the aircraft. As it gains altitude, the acceleration of gravity decreases. The changes in both mass and the acceleration of gravity impact the force of weight. As the force of weight decreases, the amount of lift required to climb higher, maintain altitude, or descend for landing also decreases. By the time the aircraft lands in Los Angeles, it is 14.5% lighter than when it took off. The weight of an aircraft is a critical variable force that must be considered when studying the science of flight and the technology necessary to develop and fly modern aircraft. In the other lessons in this section, we will be discussing the other three forces affecting flight: lift, drag, and thrust. All three are impacted by the weight of an aircraft.